Hey there, geometry fam. Welcome to lesson 7. And actually, this is going to be a short and sweet lesson on using inductive reasoning. I anticipate this one's going to go pretty quickly. We're going to do the lesson practice right away because inductive reasoning is something we have to practice with right away. Inductive reasoning is something that's near and dear to me because it is the kind of reasoning we use in science all the time. What is inductive reasoning? Why, inductive reasoning is the process of reasoning that something is true based on several specific cases. So you maybe heard that deductive reasoning, which is the counterpart to inductive. Deductive reasoning is reasoning from general to specific. You take a general rule, and then from that general rule that's always true, you can state that specific cases of that rule are true. Inductive reasoning is just the opposite. We take a bunch of individual cases that we observe to always be true every single time we test them. However, we only test a limited number of cases because we can't test every case. And if it turns out that those cases are always correct every single time we test them, then we inductively reason a rule from those specific cases. That's inductive reasoning. And the reason it's near and dear to me as a science teacher is because science uses those specific cases all the time. That's what experiments are. We do experiments again and again and again. We don't test every single possible scenario. We just do a group of experiments that confirms a hypothesis that we have. And if we confirm that hypothesis enough times, then we can come up with general rules based on our hypothesis, like theories, right? That's what inductive reasoning is, okay? There's a couple other terms we need to know. Conjecture is a statement in geometry that is believed to be true. In science, we call it a hypothesis. It's a guess, an educated guess. In geometry, we're going to state it a little bit more strongly, though. It's something we assume to be true until it's proven false. Now, keep in mind, you're going to see some conjectures that are just downright stupid, okay? That are absolutely incorrect and really easy to prove wrong. So when I say that it's believed to be true, keep in mind that sometimes the examples that we're going to be looking at are ones that are obviously false. You have to assume it's true until you come up with a counter example. A counter example is an example that does not support the conjecture. You just need one counter example to disprove a conjecture. Now, here's the thing. In order to prove that something is always true, you have to test it again and again and again and again and again. And every single time that you test it, you have to support your hypothesis. But one time, it just takes one time that you test and you find a counterexample to your conjecture. You just need one counterexample to disprove your entire conjecture, okay? So that's a really important understanding in inductive reasoning too. It takes a whole lot of evidence for you to state that something is correct based on inductive reasoning. You do a lot of experiments. You look at a lot of individual cases and examples, but it just takes one counterexample to prove it false. All right, let's take a look at some examples from the homework. The first thing we need to do is formulate a conjecture about how the next value in this pattern would be found. Now, I'm a math teacher here, so I recognize this pattern as a well-known pattern. So I'm going to talk about that in just a moment. But boy, look at this pattern. Can you figure out where the next numbers in this pattern come from? 1, 1, 2. Well, I notice that 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13, 21. 30 plus 21, 34. 21 plus 34 is 55. I'll bet we add the previous two numbers to come up with the next term. So to come up with the next term, we add the previous two numbers, previous to whatever the next term is. That's what I would say is my conjecture. Okay, now to prove that conjecture correct, we'd have to look at more data. So here we have a specific number of cases of numbers in a pattern, and from this number of cases, I've developed a rule. So I'm going to say the next number is the sum of the previous two numbers. Okay, and then that's how that pattern would keep going. Now I need to look at more and more data to know that that rule is true for sure. Now here's the thing. I recognize that rule. That's Fibonacci sequence. Fibonacci sequence is a famous sequence in numbers in math that just keeps adding two numbers and coming up with the next number. I actually used deductive reasoning because I knew the rule and I reasoned from that general rule to the specific case where I see Fibonacci sequence written on the page right here. So I kind of cheated in that case. However, you can see how you would use it inductively if you're using the cases of the numbers that are in the pattern to come up with the next one. All right, sorry, I don't mean to be a cheater, but I kind of had to be on that one. Letter B, test the conjecture that every even integer 4 through 14 can be written as the sum of two prime numbers. Oh, okay, so now I have a testable set of values because I can test every even integer 4 through 14, no problem. Let's do that. So 4 equals 2 plus 2. 2 is a prime number. Let's see. 6 is the next even integer, equals 3 is a prime number, plus 3. 8 equals, and let's see, 4 is not prime, but 3 is prime. 5 is prime. All right, 10 equals 5 plus 5. Those are prime numbers. 12 equals 5 plus 7. Those are two prime numbers. And then 14 equals 7 plus 7. Conjecture correct, okay? Now that conjecture can actually become a rule because we've proven that every single case that we can look at is correct. So now I can deductively reason that every integer 4 through 14 can be written as the sum of two prime numbers because I've tested them all. All right. Now, usually inductive reasoning is used on a larger set of data than just that. You don't just do it on a testable set of numbers. Let's take a look at the next one. How might you disprove the conjecture below? Apples, pears, lemons, and peaches all grow on trees. Therefore, all fruits grow on trees. Ooh, this rings of logic class, right? All right, so I know apples, pears, lemons, and peaches all do grow on trees. That is a factual premise. Therefore, all fruits grow on trees. Well, I just need a counter example. So I need a counter example that is a fruit that does not grow on a tree. Can you think of a fruit that does not grow on a tree? What about blues? Blueberries do not grow on trees. They grow on bushes. We could also put raspberries in that list because they also do not grow on trees. There's a lot, actually, probably most berries. I guess there's some berries. Mulberries grow on trees. But blueberries and raspberries are two common counterexamples. Okay, so what you need to understand, inductive reasoning. We reason from specific cases to a general conclusion. We try to have as many cases as possible to prove beyond the shadow of a doubt that our conclusion is correct. We would have to test every single case. In some contrived problems like letter B, we can do that. But in most real world problems, like scientific problems that scientists actually study, we can't possibly test every single scenario. We test a lot of scenarios. And if something always is true and it's a really good explanation for something, then it becomes inductively reasoned theory or a law, okay? So that's today's lesson. You should be able to answer numbers 1 through 30.